Gradient boosting is great in the sense that it allows you to combine the results from a series of weak models, and by combining the results from a series of weak models you can have a strong outcome. So you might have a weak model that produces results and then error, and then those errors can be used as the y, or the outcome variables, for a series of new models. So you might have several trees that are used to be able to fit to the error, and then amongst those trees some will be better fitters than others, and so those are given the most weight, and then that produces a series of errors, and then a new set of trees are tried to reduce those errors. And so what's happening when you're going through the boosting process is you're adding weak model to weak model to weak model, and each one is just doing an additional cumulative job of reducing the overall error. And so basically you can build a model from a series of small models. It's very fast to do and very fast to implement. An advantage, or disadvantage rather, of gradient boosting is that it's a black box, and so there's no interpretable model parameters. It really is a whole chain of trees, of short trees generally. So you've got your original model and a whole bunch of little trees that the results are put together, and so you can't really visualize it very well. There's just too many different trees to try to think about when you're looking at their completed model, even though a lot of data mining tools will show you the trees. So for example, if you go into JMP, you can see the trees. I believe Azure will let you see the trees too. So they'll show you the trees, but you don't usually want to show your manager the trees because it's just too much complexity to absorb. Random forest. The nice thing about random forest is that it really is a whole series of different whole trees. So where boosted trees was a collection of short trees, random forest is a collection of big trees. And it's often the most accurate of all the algorithms, not all the time. AND is another one that wins many more than its share in boosted trees. But random forest is really effective, and the guy that designed, the researchers that came up with random forest designed it primarily to do two things. One is that when you do, they designed it primarily to overcome the limitations that are inherent in the CART method. In the CART method, you try every single potential splitter for every single split every single time. And so basically you're looking at every splitter as a potential, or every input variable as a potential splitter for every single split. Now that's good because it's very systematic, but it's bad because sometimes the best splitter up high in the tree will mean that the overall model is not as good as if you'd used a weaker splitter high in the tree. And so the designers of this method said, let's create a system that gives weaker splitters the chance to be higher in the tree all through the tree. And so what they did is they set it up so that a small number of input variables are randomly selected from all the input variables, and from among those the best splitter is selected. So if you had 20 input variables, you might just have 4 or 5 input variables that are randomly pulled each time, and in that group of 4 or 5, then the best splitter is chosen. Then you go to the next split, and another random set of 5 input variables is selected, and among those the best splitter is chosen. And so basically what you're doing is you're making it less systematic to fit the tree, so that every time you build a tree, instead of having exactly the same tree, you have on purpose a bunch of different trees with lots of different splits, and the various input variables are forced to be at different positions in the tree multiple times. And that way you can get more variety in the trees and allow those variables that might be worse at the top but allow for better results when all the tree is taken into account to be able to participate. The other sort of bottleneck or limitations that CART creates is using the exact same data every single time. In other words, if you, in a CART model, if you partition the data in training and validation, then the same training data is used every single time. And that's a problem in the sense that you've given it one look at the data, and so it will systematically go through and create the CART tree based on that same look at the data all the time. And the researchers said, that's a problem. We want it to look at subsamples of the data when it's doing its training all of the time. so that we don't have this one deterministic view of how the tree is built every time. So when you go in and do a random forest, generally what you do is you say, I want, say, 60% of the model to be, or 60% of the data to be randomly selected each time it goes through and does a split. And so it will pull various pulls of the data, various samples of the data all the way through. What happens is that the same record has many chances to participate in the training and many chances to participate in being in the validation set. And so that happens many, many times. And so what you have is, instead of it being too deterministic, you have these different views of the data that are always being generated to be able to allow the trees to be fit. Then many trees are developed, and then you have the trees that, so let's say you have 100 trees or 50 trees developed. Then when a new instance is dropped down the trees, then it would be dropped down 50 trees, and then it would be estimated 50 times, and then the average, in the case of predicting a number, would be taken, or the most frequent outcome in terms of a category would be taken and assigned to all of the values that end up down at the bottom of the tree. And so essentially it's a voting method, and because you've voted across many trees, you are automatically taking care of the tendency to overfit. You might be overfitting on one tree but not overfitting on 49, or you might be overfitting on 10 of the trees but the other 40 are not going to be overfit. And so it's just built in. This built in to the method is controlling for overfitting, because you have many, many different trees that are being built and estimated from. Disadvantages of random forest is that there's no one interpretable model in the sense of easy to visualize, because it's a bunch of trees, and so generally these trees aren't even shown to you by the algorithms that produce them, because who wants to look at 50 trees or 100 trees? And so it's not easy to interpret. And then you also have to build many trees, and so it takes time to build lots of different trees. So KNN and random forest are the slowest methods for building models, because they're just intensive, and the more trees you build, the longer it takes to build the trees, and the more data you have, it also slows down the data, or slows down the modeling process too. So for KNN and for random forest, you generally, unless you've got lots of time, you generally only give them smaller data sets, because if you give them millions of records, then the algorithms just can take a ridiculously long time to finish. So they're great for smaller data sets. Or if you've taken a random sample of the data that represents the data, then maybe you can work on 10,000 records or 15,000 records instead of 1,000,000 records. And it's especially important to do that when you're dealing with KNN and random forests. Support vector machines are nice in the sense that they are able to see a bunch of different shapes, and they can perform very well even if you have a lot of attributes and not very many records to train from. If there's a really good pattern that can be identified, SVM can often do it, and it's one of the reasons why it's used for pattern recognition. So it's used for looking into space and finding black holes or finding planets, or in terms of trying to find oil under the earth, where they bounce radars down into the earth and try to identify the patterns that come back, because those are sort of like visual patterns, and if those patterns are sort of systematic, then support vector machines are good examples. Another good example for a support vector machine would be pattern recognition for handwriting recognition or face recognition, because they're very good at kind of looking at different shapes of patterns. So we have a bunch of different sort of looking solutions, and theoretically support vector machines can handle any of them. It can do something that looks kind of like nearest neighbor. It can do stuff that looks like decision trees. It can do stuff that are kind of linear functions, and it can also do nonlinear functions. And nonlinear functions might include things like circles, hyperbola, ovals, a variety of W shapes, a variety of different shapes, and SVM can handle lots of different sort of shapes in terms of what it looks for. Now, one of the things that an SVM does is it looks for a best separating hyperplane and the widest margins around that, and it also uses support vectors, and so you should go back and look at those slides to determine how those are done. You know, what is a separating hyperplane? What is a margin? How do you know that you've got one hyperplane that's a better separator than others? And so go back and review those slides in terms of, because I'll give you pictures and ask you what is the best separating hyperplane, what's a margin, what's a support vector, things like that. What's a kernel? You know, what is the kernel in this picture, and so forth. Not what's the mathematical function used necessarily for that kernel, but where's the kernel playing a role in doing the support vector machines. Now, kernel is a mathematical manipulation that changes the value of the x or the y variable. So if you have y equals mx plus b, that's a linear function. So one way of doing a kernel would be to convert the value of x or y so that you have a nonlinear function. And so you could use a kernel that creates a circle or an oval or a hyperbola. And so basically what a kernel is mathematically changing the values so that you might be able to find a better separating hyperplane. And there are good examples in the slide deck and the reading for that topic that you can use to sort of do that. This is computationally intensive, and it tends to overfit. One of the cool things about kernels is that there is an infinite number of kernels that could be used. But generally what happens is that one or two of the kernels will be used in any implementation. So even though you've done support vector machines, usually your implementation will have one specific kernel that's kind of a good general use kernel. But if you tried a different kernel or a different set of kernels, you might find a different kernel that was better than the one that was in your implementation. So some tools will let you try a series of different kernels, and if you don't get good results with one kernel, you can try a second, a third, a fourth, and a fifth kernel and see if you get better results for those kernels, because there's no way to automatically or theoretically or automagically be able to always pick the best kernel. So they usually use one that's just a good general use kernel.